Okay, the part two. So we're going to use graphs now to solve equations. So the biggest use of graphs is to solve stuff like equations, inequalities, stuff like that. So first of all, we can solve simultaneous equations by sketching both graphs and finding where they intersect. So the solutions of the coordinates where the two graphs intersect. So if we got asked to solve these simultaneous equations, we could type them into a graphical calculator or into a graphical online website. So GeoGebra is a good one. And now the first one would give me the straight line, and the second one would give me a circle. And the answers, so the solutions would be this point here and this point here. So roughly, that's about it's 2 point, I don't know, it's at 2.7-ish and 6.3-ish. And this one here is about minus 4.8-ish. And this one here is about minus 0.6-ish. Yeah, so I've got my estimated answers. X is 2.7, Y is 6.3, X is minus 4.8, Y is minus 0.6. However, if you want the exact values, that we will then solve them simultaneously. So the method for solving them, if you can remember, is we would try and substitute one of them into the other one. So the first one, if I number them 1 and 2, I can rearrange 1 to get y equals 4 plus x by adding x to both sides. And if I sub that into 2, I get x squared plus 4 add x minus 2 squared equals 29. Well, I can simplify that to get x squared plus x plus 2 squared equals 29. I can expand and simplify, so x squared plus, not x squared plus 4, it's x squared plus 4x plus 4 is 29. I can simplify, so I get 2x squared plus 4x, and I can take away 29 from both sides to get minus 25 is 0. And then I could solve that. So we can solve that using a calculator. Actually, does this one even do it? It does 3, so 2, 4, minus 25. So we get x is minus 2 plus or minus 3 root 6 all over 2. And one answer is x is 2.674. So that's going to be that one. So that's quite a good estimate. And the second one, the one with the minus, gives me x is minus 4.674, etc. So close with that one. And then to get the y, I would just sub them in. So when x equals minus 2 plus 3 root 6 over 2, then y, I just add 4 to that. So y would equal, so you can use your calculator, or I can write 4 as 8 over 2. So now I can just add the tops. 8 add minus 2 is 6. So 6 plus 3 root 6 over 2. Which, let's check what that is. That's decimal, see how close my guess was. 6.67, oh, so 4 off. Actually, I could just add 4 to that, couldn't I, to get my estimate. And then when x is minus 2 minus 3 root 6 all over 2, y would be, well, again, if I change that to 8 over 2, I would get 6 minus 3 root 6 over 2, which hopefully should be minus 0.674. Yeah, so I was close to that one. Yeah, so we can use graphs to kind of get estimates, and if we want exact answers, we would solve them. But lots of time in real life, estimates would be fine, so the graph method would be fine. Whereas for A-level maths, for the pure side anyway, we like exact answers. We prefer these answers with the roots and fractions as opposed to decimals. Okay, so we can also solve equations when it's just one variable. Now, to do this, we have to make two equations. So if I'm trying to solve the equation f of x equals g of x, I will draw the graph y equals f of x and draw the graph y equals g of x, and where they intersect are the solutions. So x squared minus 3x plus 5 equals 2x minus 1. So I could draw the graph y equals x squared minus 3x plus 5 and draw the graph y equals 2x minus 1. So that's what I've done here. So how many solutions are there to the equation? Well, I can see 1, 2 places where they cross. And what are the solutions? Well, since I just want the x values, I don't care about the y values, it looks like 2 and 3. So x equals 2, x equals 3. So to check that they're the exact solutions, we will just solve that equation algebraically. So take away 2x from both sides and plus 1 to both sides. To get equal to 0, I can factorize that, x minus 2, x minus 3 equals 0, and then solve it, so x equals 2, x equals 3. Now, alternatively, instead of sketching these two graphs, I could have rearranged first, and I could have sketched this graph, so y equals this quadratic, and y equals 0, which is just the x-axis, and where it crosses would give me 2 and 3, which would be the solutions. So by making it equal to 0, that's why in maths we make equations equal to 0 a lot, because it's easy to just read off roots. Yeah, you can easily read 2 and 3 there, but if I drew that quadratic, it would look something like that. So I'll easily get 2 and 3 quickly. So that's why we like stuff equal and 0 in maths. Okay, here's an example of a function. So it's kind of like an m. Now these dotted lines are just to show you that's 2 and that's 2 and that's minus 2. So it's an m. So there's my function y equals f of x. Use the graph to write down the number of the solutions that exist to each of the following equations. So if f of x was 1, well, I would have to draw the line y equals 1. So 1 would be about here. And it intersects 1, 2, 3, 4 times. So there's 4 solutions. For this one, f of x equals 3. Well, I've got the graph y equals f of x, so I need the graph y equals 3. So 3 would be up here. And there's no solutions. F of x equals minus 1. So I need to draw the line y equals minus 1. So that's somewhere down here. So that's 2 solutions. And f of x equals 0. So I need the graph y equals 0. So that's here, and the y equals 0 is the x-axis. And that crosses 1, 2, 3. So 3 solutions. Yeah, they're common questions in exam. Just how many solutions are there? And it could easily be a multiple choice question. Just use graphs. Don't try and solve it because you don't even have the equation for that. Okay. Now, before we move on to page 8, I just want to go back to page 5 a second. We've covered the stuff I wanted to cover before we could talk about this. So we've got a graph here of a function f of x. It says the domain is minus 2 to 6. So x goes from minus 2 to 6. Remember, the domain is the input. And it says a minus 2, it's 10. It hits 2, 0. And then from 2, 0, it goes to 6, 4. So write down a domain and range of f. Well, domain's given to us in the question. Let's write that as set notation. And the range of f is f, and f goes between 0 and highest output is 10. Find f of 0. Remember, f squared means f of 0. So, well, f of 0. So that means my input is 0. So my output's there. Oh, well, I don't have the equation of the line, but look, 0 is in the middle, minus 2 and 2. And so that means this is going to be in the middle of the line. So it goes from 0 to 10, so that must be 5. And then I input 5. So 5 would be here. So again, I don't have the equation of this line, but look, from 2 to 6, that goes 4 across. And this number here, remember, was 4. So it went from 0 to 4, so it went 4 up. So 4 across, 4 up. So to get from 2 to 5, it's 3 across, so it must be 3 up. So f of 5 is 3. So f squared 0 is 3. Okay, we got a function. X goes to 4 plus 3x over 5 minus x, and we want to find g inverse of x. So remember the trick, I call that letter. So I call that y, and you can see why I'm calling it y now to link with graphs. Apply g to both sides. So g of y is g inverse of x, and these cancel, so let's get g of y equals x. I want to sub in y into g, so 4 plus 3y over 5 minus y equals x. I'm just going to rearrange it. So times both sides by 5 minus y. Expand the right-hand side. Now I want all the y's on one side, so I want to plus xy to both sides. And I'm going to take away 4 from both sides. I'm going to factorize out the y. I'm going to divide both sides by x plus 3. So there we go, there's the inverse, because y was the inverse. So the inverse of g is 5x minus 4 over x plus 3. And it says solve g f of x equals 16. So again, it doesn't want me to work out the function g of f, because, well, I don't even have the equation for f. So instead, I'm going to do the inverse to both sides of g, because on this side, the g inverse and g cancel out. And on this side, g inverse of 16, well, I can just sub 16 into there. So 5 times 16 minus 4 over 16 add 3 gives me 4. So the left-hand side becomes f of x, and the right-hand side becomes 4. So if I draw my line, because I've got the equation y equals f of x, that's that. If I draw the line y equals 4, that's that. So my two solutions are there. So straight away, one answer is x equals 6. And the other answer is this bit here. Now again, I don't have the equation of the line, or I guess you could work it out. The 12 might find it tricky to work out. But we know if I just look at that line, it goes from 0 to 10. So this height here is 10. And it goes from 2 to minus 2. So that's the length is 4. But I want this height to be 4. So I can just use similar triangles. The scale factor from 10 to 4 is 2.5. So if I do 4 divided by 2.5, I get 1.6. So if I go 1.6 across, I get 0.4. So my other answer is x equals 0.4. Yeah, just from the graph, look, 6 here, because that's when it hits 4. It hits 4 here, we just use that to work out 0.4, just similar triangles. Yeah, that was the scale factor, 2.5. Or you could work out the equation of the line if you wanted to, and then you'd still hopefully get 0.4. Okay, so I can now put that page away because we're finished. So on to page 8 now. So to sketch the graph, y equals 4 over x squared, and y equals x squared times x minus 3. It says use the diagram to state, with a reason, the number of real solutions to this equation here. Well, I haven't got the graph of this, but I've got the graph of these two things. So let's see if I can rearrange this a little bit to get these two things here. So if I add 4 to both sides, and if I look here, it's 4 over x squared. So if I divide both sides by x squared, I get x squared divided by x squared gives me x squared. And I get 4 over x squared. So this equation is turned into this equation. Now I've got this graph, and I've got this graph. So 4 of x squared is this one, and the cubic is this one. And so they intersect once. So one real solution as graphs intersect once. And why do you think we use the word real here, the number of real solutions? And it's because if you did further maths and you looked at imaginary numbers and complex numbers, then there would be more than one solution. Just some of them wouldn't be what we call real. Real just means, remember, we can put them on a number line. Yeah, imaginary numbers don't go on number lines. Don't go on one number line at least. So that's why the examiners specify the word real. Okay, so here's three for you to have a go yourself. So you've got some graphs and you've got some equations. So here's these two graphs. Show that there are two real solutions to this equation. So you want to make this equation look like these two things. So you divide both sides by x. And then I've got these two curves, so the quadratic, cubic and the reciprocal, and they intersect twice. So two intersections, therefore two real solutions. Got these two. Show that there's one real solution to this equation. Well, this one looks a bit trickier. So instead I'm going to start with making these two equal, because I can see that they've got one solution, and see if I can get from there to this. So if I expand this side using binomial, I get x cubed plus 3x squared plus 3x plus 1. If I expand this, 3x squared minus 3x. Then if I take away 3x squared from both sides, they'll cancel. And if I plus 3x to both sides, I get 6x. So I get that. So one intersection, therefore one real root. And last one, 1 over x, and this minus x minus x minus 1 squared. Sure, there's no real solutions to this. Well, again, looking at the graph, I can't see any intersections. So if I make them equal, and hopefully do a bit of rearranging to get this. So times both sides by x. And then plus both sides by x squared, x minus 1 squared. So 1 plus x squared, x minus 1 squared equals 0. So no intersections, therefore no real solutions or no real roots. Okay. Inequalities, well, these can be solved in the same way as equations. So to solve an inequality, there's a few steps to it. We first of all solve the equation to get the critical values, then we use the graphs to decide which regions it is. So we sketch the graphs, y equals f of x, y equals g of x. We solve it, just like we practiced, to get the critical values. We use the graph to see when the region f of x is below the graph g of x, or it could easily be bigger than or equal to, etc. And we write the regions using either inequalities, interval notation, or set notation. So if I'm trying to do this x squared minus 6x minus 7 is bigger than 0, well, I can sketch the graphs y equals x squared minus 6x minus 7 and y equals 0. So this is my quadratic, and this is the line y equals 0. So here's my critical values. So it looks like minus 1 and 7, but let's just check. So I'm solving it. So I'm solving x squared minus 6x minus 7 equals 0. I can factorize this, x minus 7, x plus 1, 0. So x equals 7, or x equals minus 1. So I've got my critical values. So the solution, well, I just need to make sure I understand which graph's which. So this is the quadratics, this one's this one here. So I want this to be bigger than x. So after this point here, so after 7, the quadratic is bigger than 0. So after works. So the solution is x is bigger than 7. If I look in the middle between minus 2 and 7, minus 1 and 7, the quadratic is less than 0, so that doesn't work. And then if I look less than -1, the quadratic is above 0, so therefore that does work. So x is less than -1. So there it is as interval inequalities. I can write as interval notation. So 7 and infinity, or -infinity and -1. I can write as set notation x, such that x is bigger than 7, or x such that x is less than -1. Yeah, I can solve. Here's another one. So one thing I could do here, I could rearrange it to make it equal to 0, or make one side equal to 0. But I'm just going to show you it still works even if you don't do that. So if I sketch the graphs, 5 plus 3x minus 2x squared, and 1 minus 4x. So this first one's the quadratic, second one's a straight line. So here's my quadratic, here's a straight line. So I want the quadratic to be bigger than the straight line. So solve for the critical values. So I'm solving when they're equal. Now let's see if I can take a guess from the graph. It looks like this. It looks 4 is 1 and minus, I don't know, 0.5-ish. So I'm going to add 2x squared to both sides. I'm going to take away 3x from both sides. I'm going to take away 5 from both sides. So that's my quadratic. It's equal to 0, so I can easily solve it. So I'll factorize, or I'm going to cheat and use a calculator. So 2 minus 7 minus 4, and we get 4 and minus a half. So x equals 4, x equals minus a half. So here's 4, and here's minus a half. So they're my critical values. So to solve them, I just need to look at the regions. So if I look, let's start on the left-hand side this time. If I look what happens before minus a half, the quadratic is less than the straight line, so that side doesn't work. If I look what happens in the middle, from here to here, the quadratic is above the straight line, so the middle works. And if I look what happens after this intersection, so after 4, the quadratic again is below the straight line, so that side for x doesn't work. So my solution is, well, x has to be bigger than minus half and less than 4. Or I can write that as interval notation, or I can write that as set notation. Yeah, so I've just put it here. If you prefer this example, if you found this one easier to visualize because it was easier to compare with this line here, then that means you prefer 0 on one side. So you could rearrange this like we did here to try and solve that. And as long as you remember that when we manipulate inequalities, that if you multiply or divide both sides by a negative number, we need to change the direction of the inequality. Then you can also do that. So here, look, if I, well, let's do one where we have to change the sign. So let's times both sides by -1. So I get -5 minus 3x plus 2x squared minus 1 plus 4x, and the sign has to change. Then I can rewrite this as 2x squared at the front. Then I can take away 4x from both sides. That won't change the sign because I'm adding and taking away. And plus 1 to both sides, so -4 is less than 0. So I would have a quadratic, which would look like that. And I want, when is the quadratic less than 0? Well, it'll be between these 2 points here, look. So that might be easier for you to visualize. If you're happy with this, then that's brilliant. Otherwise, you might want to rearrange to get 0. Okay, and last bit about inequalities is we could have 2D inequalities. So we did this right at the beginning of the year, but you've probably forgotten by now. So the inequality y is less than f of x represents the point below the curve, y equals f of x, and we use a dotted line for y equals f of x. The one y is bigger than f of x is everything above the curve, and we use a dotted line again. So this one here would be y is bigger than f of x. This one here would be y is less than f of x. If it's less than or equal to, it's the same rules, but we have a solid line. So here's a diagram, and it shows the graphs of y equals x plus 5, so the straight line, and x squared minus 4x plus 5 is the cubic. State which pair of inequalities defines the shaded region. Well, it's less than the line, so if y is less than x plus 5, because it's underneath the line, and equals with the solid line, and it's above the quadratic, so y is bigger than x squared minus 4x plus 5, and again it's a solid line, so it's bigger than or equal to. So look at which one of these works. It's this one here. And one more for us to try. You might want to try this one yourself. Using the graph below, shading the region that satisfies y is bigger than or equal to 0. So I need the line y equals 0, and I want bigger than or equal to 0. So y equals 0 needs a solid line, and I want to be above that line. So I want to be this side. X is bigger than or equal to minus 2. So there's an equal sign there. So on x equals 2, I have a solid line, and I want to be bigger than minus 2. So I want to be on this side of minus 2. So above here and above here. So far that's this big square. Y is less than 5 minus x. So this line is 5 minus x, and it needs to be dotted still. And so I want to be underneath that line. So far it's this little triangle. And y is less than or equal to 7 minus x squared. So that's the cubic, and it needs to, quadratic, and it needs to be a solid line. And I want to be underneath it. So I want to be underneath the quadratic, underneath this line, and above this line, above this line. So it's this bit here. Yeah, and that's all there is to it. So I'm going to stop part 2 now